In the last lecture, we studied current density J is equal to N, which is concentration of electrons, multiplied by Q, which is the charge on an electron, multiplied by velocity. This equation which we derived was meant for conductors. Now, we will talk about current density in semiconductors. We have actually two different types of current density in semiconductors. One is drift current density and other is diffusion current density. The equation which we learned in the last lecture was of actually drift current. If you want to understand the difference between drift current and diffusion current, then assume that we have a semiconductor, and if an external battery is applied producing an electric field inside the semiconductor and the current is caused due to the electric field only, then the resultant current density is drift current density. However, let us assume that we have a semiconductor and somehow at one end of the semiconductor we have created charge carriers in excess, whereas on the other side we have comparatively a smaller number of charge carriers. For example, you can assume that we have a device that releases photon, and this photon bombardment at one end of the semiconductor results in excess charge carriers with respect to the other end. However, these charge carriers will not be stable at that moment, since the concentration of charge carriers at the right end is greater than the left end. Then these carriers will try to move in the left direction, trying to balance concentration of charge carriers in the semiconductor. This movement of charge carriers result in diffusion current, and such type of current density is referred as diffusion current density. We will talk about diffusion current density in the next lecture. In this lecture, we will focus only on drift current density. In conductors, we have only one type of charge carriers, which is electron. However, for semiconductors, we have electrons as well as holes. So, drift current density caused due to electrons is N0, which is the concentration of free electrons in the semiconductor, multiplied by magnitude of charge on an electron, multiplied by magnitude of drift velocity of free electron. Similarly, we have drift current density for holes to be equal to P0 multiplied by Q multiplied by drift velocity of holes. You need not to get confused about why we have taken Q for charge on an electron as well as charge on the hole. Some of you might think that we should take minus Q in drift current density for free electrons. The thing is, drift velocity is a vector quantity. For example, if we take a semiconductor and apply an external battery such that the electric field is from right to left, then the drift velocity for holes will be in this direction, and for electrons it will be in this direction. So, if we put positive sign towards the electric field and negative sign opposite to the direction of electric field, then we will get drift current density for free electrons to be N0 multiplied by minus Q multiplied by minus VDN. Two negative signs will cancel each other, giving us N0 multiplied by Q multiplied by VDN. That's how we get drift current density for free electrons and holes to be of the same sign. You should not go ahead to next lectures unless it is clear to you that the current density for free electrons and holes is in the same direction. I will try to find another way to make this particular point clear in the next lecture. Now, the net drift current density comes out to be summation of drift current due to free electrons plus drift current due to holes. This is the final formula for finding the net drift current density in a semiconductor. However, you also know that drift velocity is actually equal to mobility multiplied by electric field. So, we can write drift velocity for free electron to be equal to mobility of free electron multiplied by electric field, and drift velocity for holes to be equal to mobility of holes multiplied by electric field. By putting these values of drift velocity in the drift current density, we will get. Now we will separate the electric field component from the two terms. If you remember, in earlier classes you might have already studied that we have a formula: current density is equal to conductivity, which is denoted by sigma, multiplied by electric field. By comparing these two equations, we will get conductivity for semiconductors to be equal to free electron concentration N naught multiplied by the magnitude of charge on a free electron multiplied by mobility plus hole concentration multiplied by magnitude of charge on a hole multiplied by mobility of holes. And another formula which you might be familiar with is resistivity rho is equal to 1 upon conductivity. Another very simple formula is resistance R is equal to resistivity multiplied by length of the semiconductor divided by area of cross section of the semiconductor. By using these formulas, many questions can be framed. That's all for this lecture. I will see you in the next lecture in which we will discuss diffusion current density.